Today I am going to discuss about advanced data structures and algorithm analysis. In that subject, I am going to discuss about uh, NP hard graph problems. In that, the first one is a click decision problem. The second one is a chromatic number decision problem. Third one is traveling salesperson decision problem. And fourth one is job shop scheduling. Okay, these are the topics I am going to discuss now. First one is a click decision problem, and second one is a chromatic number. Third one is traveling salesperson problem, and fourth one is job shop scheduling. Here the question is why you are called as a click decision problem as a NP hard, and similarly why you called as a job shop scheduling as a NP hard problems. Okay, once you look at the first topic, click decision problem. Before going to discuss about click decision problem, first you have to know the what is a complete graph. Okay, you have to understand the click decision problem. You have to idea about complete graph. We will see what is a complete graph. A graph is said to be a complete graph if there are edges from any vertex to all other vertices present in a graph. That is called as a complete graph. Okay, complete graph means in graph, each and every vertex is connected to all other vertices present in a graph. Once we look at the example K3 graph, here three vertices are there, A, B, and D. Okay, in that A is connected to B and also D. Okay, similarly, B is also connected to A and B is also connected to D. Similarly, D is also connected to A and B. Okay, this is a complete graph. Okay, in that graph, A is connected to remaining vertices, and also B is connected to remaining vertices, and D is connected to remaining vertices. That is called as a complete graph. Okay, before going to discuss about click decision problem, we have to know the what is a complete graph. Okay, now we will see what is a click. Okay, click is a subgraph of a graph such that all the vertices in the subgraph are connected with each other. That is a subgraph. It is called as a complete graph. Okay. Here the click is a subgraph. That is a complete graph. Okay. What is a click means? Click is a subgraph of complete graph. Okay. In that, here next one is what is a decision. Okay. Up to now we have discussed about what is a complete graph and then click. Next one is what is a decision. Okay, what is a decision problem means you can say that two options. Okay, either yes or no or one or zero. That is called as a decision. Okay, in that you have completed a click and decision. Next one is why it is called as a NP hard and NP complete problem. Why click decision problem is called as a NP complete problem. Now we will see. Okay, here the next one is what is a problem definition. Here we are going to given the input as a subgraph of graph g equal to b comma e and integer k. Here the output is s if the click exists, okay, or no otherwise. Okay, in output either yes or no. Yes means click exists, no means not exist. Okay, next one is a click. Okay, what is a click means? A subset of vertices where every pair of vertices is connected by edges. Okay, here the question is, does there exist a click of size k in the graph? Okay, here the question is if the click size present in a graph or not. Okay, next, these are the some examples of click. Okay, here two graphs are there, or two figures are there, figure 1 and figure 2. First, once you look at the figure 1, okay, here two clicks are there. Okay, one is click size of 3 and second one is click size of 2. Okay, similarly, you look at the figure 2, here also two clicks are there. First one is click size of 4 and second one is click size of 3. Okay, like that you can say that click. Okay. Next one is why the click decision problem belongs to NP hard. Okay. Now we are going to prove that click decision problem is a NP hard. Okay. Here the question is why the click decision problem belongs to NP hard. Okay. Now we are going to prove that click decision problem belongs to NP hard. Prove that Boolean satisfiability problem reduces the click decision problem. So options are once we look at the Boolean expression f equal to x1 or x2 and x1 bar or x2 bar, x1 or x3, where x1, x2, x3 are the three variables, and the cap denotes the logical and v denotes logical x. Okay, now we are going to prove that why the click decision problem belongs to the NP hard. Okay, once you look at the vertices, three vertices in a click x1 comma 1 and x2 comma 1 and x1 comma 2. Okay, sorry for the disturbance. Now we are going to prove that why NP hard belongs to the why the click decision problem belongs to the NP hard. Okay, once you look at the graph, this graph coming from this equation. Okay, how to construct this graph means in that graph, three vertices are three clicks. Okay. Once you look at the vertices, x1 belongs to 1, x2 belongs to 1. Similarly, x1 belongs to 2, x2 also belongs to 2, and x1 belongs to 3, x3 belongs to 3. Like that, we are going to construct this graph. Here, the question is we connect these vertices so that no two vertices belong to the same class are connected. No variable is connected to its complement. How to connect vertices to edges? Here the two conditions are there. First one is no two vertices belongs to the same class or not connected. The second condition is no variable is connected to its complement. Okay. What is complement means x1, x1 bar, x2, x2 bar, x3, x3 bar. That is the one condition. And second condition is no two vertices belongs to the same class or connected. Okay. Like that, we are going to construct the graph. Now we are going to check the maximum click size. In that graph, maximum click size is 3. In that classes also 3. Okay, so we can prove that click decision problem is a NP hard. Therefore, the click decision problem is also NP complete problem. Okay. Next one is chromatic number decision problem. Okay. Before going to discuss about chromatic number, first we have to know the graph coloring. Okay. You have to understand the what is a chromatic number decision problem. Before you have to know the what is a graph coloring. What is a graph coloring? Generally, graph coloring can be described as a process of assigning colors to the vertices of a graph. Generally, in graph coloring, we are going to assigning colors to the vertices of a graph. Here, the condition is that same color should not be used to fill the two adjacent vertices. We can also call graph coloring as a vertex coloring. Okay, here we are going to color the vertices, but the condition is no two uh, adjacent vertices having the same color. Okay. In graph coloring, we have to take care that a graph must not contain any edge whose end vertices are colored by the same color. This type of graph is known as a properly colored a graph. Okay. Next one, here some of the examples of graph coloring. Here I am showing that one graph is there. In that graph, we are showing the properly colored graph, which is described as the follows. Okay, in that graph, maximum number of colors are five colors. Okay, here the condition is no two adjacent vertices having the same color. Okay, once you look at the graph, here no two adjacent vertices having the same color. Okay, five different colors adjacent vertex having the same color. Okay. The above graph contains the same points, which is described as follows. The same color cannot be used to color the two adjacent vertices. Hence, we can call it as a properly colored graph. Okay. Next, we will see what are the applications of graph coloring. These are the some of the applications of graph coloring. Okay. First one is assignment. Second one is map coloring. Third one is scheduling the task. Fourth one is Sudoku. Next one is preparing timetable. Last one is conflict resolution. Okay. These are the some of the applications of graph coloring. Generally, we are discussed about what is the graph coloring means. Here, we are going to assign the colors to a vertices, but the condition is no two adjacent vertices having the same color. Okay, you can elaborately see that what are the different applications of graph coloring. Okay, first one is map coloring. Okay, once you look at the map, okay, no two, this is the Indian map, India map. Okay, here the condition is no two states having the same color. Okay, once you look at the map, okay, you colored the map for different states, but the condition is no two states having the same color. Once suppose, for example, I am giving the same color of adjacent states also. Okay, you got confusion. Okay, like that you can separate the states by coloring. Okay, that's why I am applying the graph coloring concepts to India states. Okay, next one is Sudoku. Sudoku game also different square shapes also are there. Okay, but the condition is no two boxes having the same color. Once you given the same color means you got confusion. Okay, similarly, this is my timetable. In the timetable, I am also assigning some colors, but the no two sections having the same color. Okay, once you got the same color applied to the different same section, different sections, you got confusion. Okay, like that I am giving the different color. Okay, next one is chromatic number. Up to now we are completed what is a graph coloring. Next one is chromatic number. Okay, what is a chromatic number means? A chromatic number can be described as the minimum number of colors required to properly color any graph. Okay, suppose we are going to coloring a graph. Here the condition is what are the minimum number of colors you are following to coloring a graph. Otherwise, in other words, a chromatic number can be described as a minimum number of colors that are needed to color any graph. Okay. In graph coloring, chromatic number means minimum number of colors that are needed to color any graph. Okay, these are the examples of chromatic number. Once you look at the graph, how many different colors are there? Three. Okay, so the chromatic number of this graph is three. Okay, why it is called as a three means here I am applying three different colors to a vertices. Okay, that's why this graph chromatic number is 3. Okay, next one is types of chromatic number of graphs. Okay, we have so many different types of graphs. First one is a cyclic graph. Okay, what are the cyclic graph? Okay, what are the chromatic number for cyclic graph? Okay, but first we will see what is a cyclic graph. Simply cyclic graph having the cycles. Okay, a cyclic graph having the path or loop. Okay, that is called as a cyclic graph. Now we will see how to calculate the chromatic number of cyclic graph. Okay, if number of vertices in a cyclic graph is even, then chromatic number is 2. The number of vertices in a cyclic graph is odd, then the chromatic number is 3. How to find out chromatic number for cyclic graph? Okay. Uh, if any graph, the number of vertices is even number, then chromatic number automatically 2. Okay. If the any graph from number of vertices is the odd number. Suppose, for example, a graph having the 5 vertices, 3 vertices, or 7 vertices, or 9 vertices. On that case, the chromatic number is 3. Okay. Once you look at the example graph also, you will see first graph having the 3 vertices. 3 is a odd number. So, chromatic number for odd number is 3. Okay. A graph having the vertices of 4, the chromatic number is 2. 4 is a even number, chromatic number automatically 2. If the number of vertices present in a graph is even number, then chromatic number is 2. If the number of vertices present in a graph is odd number, then the chromatic number is 3. Like that, you can calculate the chromatic number for cyclic graph. Next one is planar graph. What is a planar graph? Means a graph that can be drawn in a plane such that none of edges cross each other. Chromatic number of any planar graph equal to less than or equal to 4, but not exceed the number 4. Okay, all the below cyclic graphs are the planar graphs. Once you look at the planar graphs, chromatic number of each graph is less than or equal to 4. These are the some planar graphs. You will see that chromatic number below 4 are equal to 4. Okay, that is the planar graph. Next one is complete graph. What is a complete graph means? Already you will see in clickation problem. Okay, already discussed in clickation problem. What is a complete graph? A complete graph is a graph in which every two distinct vertices are the joined by exactly one edge. Similarly, simply a graph is a graph in that each and every vertex is connected to all other vertices present in a graph. Here the question is, what is the chromatic number for complete graph? Chromatic number of any complete graph equal to number of vertices in the complete graph. Okay, it is equal to number of vertices present in a graph. Once you look at the first graph, graph having the four vertices, chromatic number automatically 4. Second one, once you look at the second graph, graph having the 5 vertices, chromatic number is 5. Like that, you can calculate the chromatic number for complete graph. Okay, it is equal to number of vertices present in a graph. Okay, next one is here the question is why chromatic number is comes under NP hard problem. How can you say that chromatic number is a NP hard problem? Okay, here no polynomial solution for calculating the graph coloring. No efficient algorithm to decide if graph is K colorable. And also easy to check or to find valid coloring. Okay. Up to now, there is no simple algorithm or a different algorithm or efficient algorithm to decide the graph coloring. Okay. That's why you can say that NP hard is a chromatic number problem or graph coloring is a NP hard problem. Okay. Next one is a traveling salesperson problem. Okay. What is a traveling salesperson problem means? A traveling salesperson problem having a salesman and set of cities. Now, what first we have to discuss about what is a traveling salesperson problem. Okay. Traveling salesperson problem having the two things. First one is a salesman, and second one is a set of cities. Here the condition is the salesman has to visit every one of the cities starting from a hometown and return to the same city. Okay, here the two things are there. First one is salesman, and second one is a cities, number of cities. Here the condition is the salesman has to visit every one of the cities starting from the hometown and return back to the same city. Here, the challenge of the problem is that traveling salesman needs to minimize the total length of the trip. Okay, that is the challenge of of this problem. Okay, once you look at the general example, a newspaper agent daily drops the newspaper to area assigned in such a manner that he can has cover to the all the vertices or all the houses in a respective area with minimum traveling cost. Okay, compute the minimum traveling cost. Okay, what are the general examples for traveling salesperson problem is a newspaper agent daily drop the newspaper to expected assigned areas and starting from the hometown and return back to the covered fall city all houses and native coming back to the hometown or home city. Okay, here the what is the problem definition for traveling salesperson problem means a salesperson must visit exactly city once one time and return to the starting city traveling at the minimum possible cost and the traveling salesperson is a classic NP hard problem. Find the shortest possible route that visit each and every city from the starting position. Okay. How can you solve the traveling salesperson problem? Here I am going to discuss about a simple matrix example. Okay, in that four cities A, B, C, and D, I am going to draw the distance matrix. Okay, from A to A. Okay, all diagonals are zero. Okay, A from A to A distance is zero. B to B distance is zero, and C to C distance is zero, and D to D distance is zero. Okay. Suppose, for example, I want to calculate the distance from A to B, 10. Suppose, for example, I am going to calculate the distance from D to A, 20. Okay, and D to C, 30. C to A, 15. C to B, 35. Like that, you can calculate the distance from one city to another city, or one vertex to another vertex. Okay. Here the simple explanation of a matrix. Here the number of rows and columns according to the distance from city I to J. Okay. For example, in that matrix, distance from A to B 10, distance from B to D 25, distance from C to A 15. Okay. All diagonals are assumed as zero because distance from a city to itself is zero. Okay. Next one is the goal of traveling salesperson problem. What is the goal of traveling salesperson problem means? Here the main goal is starting and ending vertex at the same city. Suppose, for example, I can assume that A is a starting city. Okay, it is a ending city and starting city are the same. Next goal is visit all the other cities exactly one time. Okay, these are the some possible routes from starting from A, okay, A to B, B to C, C to D, D to A. Okay, in that matrix, what are the possible routes from starting vertex A? Okay, A to B, A to C, B to C to D, and D to A. Similarly, A to C, D to B, and D to A. Okay, these are the some possible routes from starting. Here the question is what is the minimum distance? Okay, in that two minimum distance are there, or two 80 kilometers are there. Okay, this is considered as a shortest possible routes A to B, B to D, and D to C, and C to A. Similarly, A to C, C to D, and B to A. Okay, you can say that simply two possible routes are the shortest distance from vertex A or starting vertex starting city. Okay, so it is considered as a minimum cost 80 kilometers. Okay, the conclusion is what is a traveling salesperson problem? Finds the shortest possible tour to visit every city wants to return back to the starting city. Okay, next one is the question is why traveling salesperson problem is NP hard. Okay, how can you say that traveling salesperson is NP hard problem? Okay, the factual growth of possible routes is the main reason why the traveling salesperson problem is considered as a NP hard problem. Suppose a graph having the four cities, its possible routes are three factorial. Suppose for a graph having the five cities, possible routes are 24. A graph having the 10 cities, possible routes are 9 factorial. A graph having the 20 cities, 19 factorial. A graph having the 50 cities, okay, that is 49 factorial. It is very big number. Okay, so we are not calculating the all possible routes of 50 cities or 100 cities. So you can say that traveling salesperson problem is also considered as a NP hard problem. Okay, there is no exact algorithm to find the shortest, shortest route from starting vertex to ending vertex. Suppose, for example, if the cities are more, okay, four cities, you can easily calculate it. Or five cities also, 24, you can easily calculate it. A graph having the 10 cities, 20 cities, 30, 40, 50, like that. For a larger number of cities, exact solutions are not practical. So approximation algorithm also not far to the optimal solution. So you can say that traveling salesperson problem is also a NP hard problem. Okay. Next one, last one, last topic, job shop scheduling. Okay, what is job shop scheduling? Okay, job shop scheduling problem is defined by set of jobs that must be exceeded or executed by set of machines in specific order for each job. Generally, job shop scheduling problem having the set of jobs Jobs must be executed by set of missions in a specific order. Each job has defined execution time for each mission and defined processing order of missions. The missions can only execute a job at a time. And once started the mission can only execute a job at a time. Once started, the mission cannot be interrupted until the completion of a assigned job. Simply, we can discuss about job shop scheduling. What is a job shop scheduling? Okay, in job shop scheduling, having the two important things: set of jobs and also missions. Okay, you can applying some missions or some missions. You can perform some jobs. Okay, here the question is each job having the execution time and also each job having the processing order of machines. Okay, here the conditions are in job shop scheduling are two conditions. Each machine can only execute the job at a time. Once the started, there is no interruption between the jobs. Okay, next one, our objective is to minimize the make span. Here, what is the objective of job shop scheduling? Maximum completion time among all jobs. We are going to minimize the make span. Make span means maximum completion time among all jobs. Okay. For instance, suppose we have three missions and three jobs. The processing order of each job as follows. The processing time of each job in mission between the currency. These are the some possible processing order of three jobs. Job one, mission three, mission one, and mission two. Job two, mission two, mission three, and mission one. Job three, mission two, and mission one. These are some possible processing orders. Okay. Next one is granted. Below are the two at least two feasible schedules. Okay, for three jobs, these are the three two possible grant charts: mission one, mission two, and mission three. And suppose the processing order of processing time, execution time 1 to 15. Okay, for three jobs, two possible grant charts I am displayed. Okay, mission one executed in job time slot three, time slot 9 to 10, and time slot three. And mission two executed by job one by 4, job two by 6, job three by 12, job three by 14. Mission three, job one by 1, job two by 7, job three by 11. Okay, once we look at the second grant chart also, okay, job three, job one, job two are overlap. Job two, job three also overlap. Job three, job one, job two also overlap. Okay, here the question is what is the make span time is very simple or very minimum. Okay, one possible schedule is the shop scheduling is not optimal. The total completion time make span is relatively large. For example, you can see idle times gaps on the machines. The large job finishes the closest time 15. If the question is among the two Gantt charts, what is the best solution? Once you look at the first Gantt chart, it takes more time. And once you look at the second Gantt chart, you can say that it is a best solution. How can you say that it is a best means? You can complete the three missions and three jobs within the time span of 7. Okay. Once you look at the first chart, you can time span of 14. Okay. So simply you can say that second one is a best or minimum or best solution. Okay. Next one. What about bottom diagram? In the second branch chart, jobs are overlapped. Ideal times also reduced. A total completion time also somewhat smaller, around 10 to 11. This represents an optimal schedule to achieve a better sequencing. Okay. Once you look at the two charts, first one is it takes more time. Second chart is somewhat better than the first one. It completion of three jobs with a time slot of 7. Okay. Once you look at the first diagram, three jobs are performed with time slot of 14. So what is the best solution is second chart. Okay. Next, what is the challenge here? What is the challenge here? Why it is related to NP hard problem? Okay, why job shop scheduling comes under NP hard problem? Okay, there are many possible sequence of jobs on each mission. for n jobs and m missions, the number of possible schedules grows factorially. Okay, so suppose for example, three jobs, three missions, you can solve easily. Okay, finding the minimum make span, smallest total completion time also somewhat variant. Okay, even verifying that a given schedule, it is feasible to easy or polynomial time, but finding the best one is computationally difficult. Why it is called as a job shop scheduling called as a NP hard problem? Okay, the question is why NP hard problem comes under job shop scheduling or job shop scheduling comes under NP hard problem. Okay, you can increase the machines or you can increase the jobs. It is difficult to complete the all the jobs in a specific missions. Okay, two jobs, two missions you can solve very easily. Three jobs, three missions easily. Four and four missions you can solve very easily. Suppose for example, 100 missions, 1,000 missions. Okay, 2,000 missions like that you can somewhat hard. Okay, so you can say that. NP job shop scheduling also a NP hard problem. Okay, thank you.